Hello everyone, this is lecture number 14 on, we're continuing the discussion on projections into a subspace, in particularly the column space of a matrix, and we will review with some more details least squares, and then summarize also the Gram-Schmidt orthogonalization process. So in some ways, we're going to be reviewing some of the things we heard in the last two lectures and provide some of the details that we missed in those two earlier lectures. As always, everything we discuss can be found with lots of fine details in Professor Strang's textbook, in particular chapter 4. All right, so let me discuss a little bit about orthogonal projections. And first, I'm going to give you a summary of the things we're going to see. So in some sense, if you understand the summary, you will understand many of the follow-up slides. And then we will go back to revisit these summary statements with a few more details. So the first thing we're going to see is projecting a vector B onto a line that is parallel to the vector A, and we're going to derive this formula that you see here. All right, so this is the projection of the vector B in the line A. You may have seen this based on elementary calculations, but we're going to revisit this calculation. So obviously, when you project vector B on a line A, you have an error that if you are thinking of approximating B with its projection P, so the error is B minus P that you see in statement 2, and the error is perpendicular to A. So using Pythagorean theorem, you can see that the projection, the magnitude of the projection square plus the error square basically gives you back the magnitude of B square. So we're going to see this, and we're going to actually find the optimal, if you like, projection so that we minimize the error of the approximation. We will generalize this to not just projecting a line, but projecting in a subspace S. So we're going to find the closest vector P to a vector B in a subspace S. So P is in a subspace S and approximates the vector B. And now B minus P is going to be our error, and that error is going to be orthogonal to S. So it's going to be on the what we have called before the orthogonal complement of S. In particular, we're interested when this subspace is the column space of a matrix A, and we would like to do in that case a projection to the column space of a matrix A, and so we will, when we do that, we will come up with the least squares approximation. So in those type of calculations, we will see that somehow naturally the matrix A transpose A is coming, and we will need to invert that matrix, and to be able to do that, we will need basically to start with a matrix A that has columns that are independent. We will show in the slides later on that the null space of A is the same as the null space of A transpose A. So to make A transpose A invertible and being able to define this least square solution, we need to be sure that the null space of A contains only the zero vector. So it will, when we do the derivations and the projection to the column space of A, the projection of B is going to come up to be this nice vector that you see in here. So from there, we're actually going to be able to define the projection matrix P that you see in here. And we're going to discuss what a projection matrix is and what the properties we anticipate. So one of the particular properties that we will see is that P squared equal to P. And you may be able to see right away why P squared is equal to P, because if you project on the column space, let's say, of A, and you take that projection and you project it once more, you will remain where you are, because the projection, if you're already on the column space, the vector you have remains unchanged. Okay, so obviously projecting twice is equal to P, and we will see this calculation as we move in this presentation. Also, you can see that if you take the transpose of P from this expression, you can see that P is a symmetric matrix. P is equal to P transpose. Okay, so let me introduce some trivial examples of projection matrices. So I'm going to take a vector B in 3 dimensions, components x, y, z, and I'm going to do 2 projections in 2 orthogonal subspaces. So in one of the subspaces would be the z-axis. So the projection P1 takes me to the z-axis, and you can see from x, y, and z, my new projected point is 0, 0, z. And the second projection is to the xy plane. So from x, y, and z, I go down to a vector that has components x, y, and 0. So this is happening with a projection matrix P1. We will see how it looks like. And this is happening with a projection matrix P2. You can actually derive both these projection matrices P1 and P2 through common sense type of statements. So we will do that in the next slide. But for the notation, note that capital P define the projection matrices, and this bold little p define the projections of B to the 2 subspaces. All right, so let me give you next the projection matrices P1 and P2 to the z-axis and the x and y plane. So you can immediately see that the matrix P1 is 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. If you multiply this with the vector x, y, z, you basically only keep the z component of the vector x, y, z. Now, don't forget, right, that we are in 3 dimensions, and when we project, we're still in 3 dimensions, but in different subspace within 3 dimensions. So this vector 0, 0, z that you see here is in 3 dimensions, but is in the subspace that is defined by the z-axis here. Similarly, the projection to the xy plane, this projection P2 is given by the matrix that you see here. And if I take actually the vectors x, y, z and I operate with P1 and P2, we get these projection points P1 and P2 that we saw in the earlier slide as well. And you can see operating with P1 on x, y, z, I only get this vector with only the z component. And projecting on the xy plane, I only get this vector where the z component now has disappeared. You can actually immediately see that because these 2 subspaces are orthogonal to each other, if you add them, if you add P1 and P2, you actually do get the whole vector B, which means if you add the projection matrices P1 and P2, you do get the identity matrix. And I believe the next slide most probably summarizes this. Yep. So we can see the summary here that you see on the bottom. The sum of the projected points give you the whole of B, and then the projection matrices P1 and P2 give you the identity. Now keep in mind that we have come up with this conclusion here because the 2 subspaces where we project are basically orthogonal complements of each other. Okay, so that's something we anticipate to see in this type of calculations. Okay, so let me mention the following. Let's take these matrices A2 and A3 that you see in this equation here, and let's say we're going to project a 3-dimensional. We're going to project a vector basically in the column space of these matrices. So the matrices, obviously A2 and A3, they look very different, but you will agree with me that the A2 has two independent columns and A3 has two independent columns. And so effectively, you anticipate that the projections that you get are identical to both the column space of A2 and the column space of A3. So for any vector, basically the projection points P2 and P3 will be the same, and also the projection matrices P2 and P3 will be the same. So remember that what you're interested in is the space itself where you do the projection, and you remember the space, the subspace where you do the projection can be generated by many vectors that effectively give you the same projections at the end of the day. So again, in this case, it's rather simple to see this because both matrices have two independent columns. All right, so we're effectively projecting in the same subspace that is spanned by the corresponding columns of these two matrices. Okay, let's move on to that formula that we saw early on projecting in a vector in a line. So here is my line defined by this vector A. This vector is not a unit vector in general, and we want to find the projection of B to that line. So what I'm going to do is I'm going to write this the projection vector P as some scalar that I denote here x hat times the vector A. I mean, we agree that P is in the direction of A, so we're going to write the projection as some parameter to compute, which we call it x hat times the vector A. So if we compute the error that we do when we have this approximation, and I refer to this as an error because in essence P is the approximation of B in the subspace generated spanned by A. Okay, so B minus P is the error. So you will agree with me that B minus P is perpendicular to the vector A. So I'm going to use that in a mathematical way. So if I define the error of B and P, and I call it E, the dot product of this error with the vector A is equal to 0. And if you follow the algebra, then you can compute that this x hat is nothing else but A transpose B divided by A transpose A. And then you can immediately see that the projection point is A transpose B divided by A transpose A times A. In many ways, this may look very familiar because if you look carefully on this formula, so this formula has A transpose A, which is the magnitude of A square. So A over one part of the magnitude gives you a unit vector in the direction of A, and then this A divided by the magnitude gives you also the projection of B in the unit vector in the direction of A. So in some sense, this formula tells you project B in the unit vector in the direction of A times the unit vector in that direction, and that's exactly what this formula is all about. But obviously here we write this in a more general form without having to bother about unit vectors. We do a projection to any vector A, and this projection takes this very nice form that you see here. All right, so let me give you an example. If it happens that the vector B is in the direction of A, you can immediately see A transpose B and A transpose A cancel, and then you get that the projection point is the same vector that you started with, all right? So that is not surprising. And secondly, if B is perpendicular to A transpose B is equal to 0, so the projection point is 0. All right, so these are the two extreme cases to consider. So let me do one example. If we have a vector B that you see here as 1, 1, 1, and we try to project it to a vector 1, 2, 2. So we are going to try to compute this x hat to find the projection point. And if you compute A transpose B in this case is equal to 5, A transpose A is equal to 9, and then immediately you see that the projection is 5 over 9 times the vector A. Okay, so that's a nice formula that doesn't involve any square roots, and that's the projection, the nearest point basically in the direction of A that we can use to approximate B. So again, this is the projection point P. If you want to calculate the error, you can subtract B minus P and you can get this vector. And you can easily check that your calculation is correct because this error has to be perpendicular to, so the error has to be perpendicular to the vector A. So if you take the dot product of E with A, you can actually see you're going to get 4 minus 4 minus 4 over 9. You get E transpose A equal to 0. So that's a nice checking on your calculations. Let me just say something on the calculation of this projection. So as you notice, we try to be general. We did not use any trigonometry here. If you really want to use trigonometry and to involve the angle theta, and you literally want to take the projection of B, using this cosine of theta, and in that case, what you will see happening is you will be getting a lot of square roots because these square roots are going to be coming from two places. One of them by calculating the magnitude of this vector A, and the other by calculating the cosine of this angle. The nice thing that we get working directly with this formula is there are no square roots coming in, so the results look way nicer directly without having to bother with computing any square roots. So you can read further on this slide, but most probably what you see on the slide is what you used to do in computing projections into a vector. Here we have generalized this formula, as you can see with this nice equation up there. All right. So the projection metrics that for this particular problem to align can be easily identified. If we look at this equation, this gives me the projection point P, all right, and you can extract from this equation this matrix A transpose divided by A transpose A. That's our projection matrix P, okay? And I remind you that A transpose, or O times a column vector, is a matrix, right? It's an M by M matrix if I work in RM. And of course, is a rank 1 matrix that has columns and rows that are multiples basically of this vector A. So the column space of this projection is generated by the vector A, and so this is a rank 1 projection metric. All right, so we not only have the projection point, but now we have the projection metrics to align. So remember this nice calculation, and actually when we generalize this to projection in the column space of a matrix, you will see that the equations will look very, very similar, but instead of a vector, we will get something else involved up there. So we will revisit this calculation in a few slides from now. So let me give you an example that solves the calculation of the projection metrics. So if I project to a line passing, this line A is 1, 2, 2, and we plug into this nice equation for capital P, we can do the multiplications, and here is the projection matrix. And you can appreciate that the column space is basically spanned by this vector 1 to 2. Every column is multiple of that. And also you can see that the row space is also spanned by the 1 to 2, and every row is a multiple of that. Okay, so this is a nice calculation. You can, if you are curious to verify that this is a projection matrix, you can actually multiply this with any vector and see what you get if you actually get something projected on the vector A. You can actually take a vector and project it twice. You can verify that p squared basically is equal to p, as we stated before. And let me just point also to some nice fact here. If you take the diagonal matrix, diagonal elements of this projection matrix, and you sum them up, you actually do get 1. So you may want to start thinking if this is something you can actually prove, or it's something that you expect in these calculations. All right. So the capital P matrix projects a vector B to the line A. The question is, what does I minus P project? So obviously I minus P will project to the orthogonal complement of that line. All right. So it will be projecting effectively on the plane that is perpendicular to the line. And if we want to generalize, it will actually project in the left null space, because effectively, you know, if we look at this as you remember, as we look at this as the column space of this rank 1 matrix generated by the vector A, I minus P will actually gives us the error, and the error is in the left null space. Okay, so maybe I'm running a little bit ahead of myself here, but in case we forget, when we discuss about the projection in the column space of any arbitrary matrix, so if P projects to the column space of a matrix, then I minus P has to project on the left null space. So remember this, because it's going to be useful in homework problems and exams, and also in understanding what these projections are all about. All right, so let's keep moving and discuss about the projection in a column space of of a matrix. So let's say we have a matrix that has columns A1 to AN. So A is M by N. So in principle, we like to think of this as projection to column spaces, so we can make a connection with the 4 fundamental spaces, subspaces of A. But in general, you can think somebody gives you a set of vectors A1 to AN and says, find me the projection of a vector B to the subspace generated spanned by A1 to AN. Now, we're going to make these vectors to be column vectors, so in essence, the subspace they span is the column space of that matrix A, and we're asking, find the projection of B to that column space of A. So I don't forget, we're going to assume that these vectors A1 to AN are independent. And I remind you, when I gave you the general introduction to this lecture, I mentioned that this would be an essential method, an essential element to allow us to carry on the calculations. We need to be sure that that matrix A transpose A that's going to come to play a role in our calculations is invertible, and for that to happen, the null space of A has to be the 0 vector, or equivalently, these vectors A1 to AN have to be independent. So the calculation of the least squares equations is rather trivial, so I really want you to fully understand the concept and being able to just geometrically come up with the answer without having to remember any equations. So what's the idea, right? We are having a vector B. This is the, let's say, the column space of A. So we need to find the approximation of B in the column space. So we write this approximation AX hat for some X hat. All right, so you remember A times X gives you a combination of the columns. So B is in the column space of A. And so we need to find an X hat, all right? And the question is, what equations do we have that will allow us to compute this best approximation of B in the column space? And the answer is we're going to take right away that this error that we commit, which is B minus P, is orthogonal to this column space of capital A. So basically the error has to be orthogonal. Okay, so let me write this. So remember the subspace that is orthogonal to the column space. What is the subspace that's orthogonal to the column space? Is the left null space. Okay, and so effectively B minus AX is on the left null space, which means that B minus AX is orthogonal to each of the rows of A transpose, and those are nothing else but the first column transpose and the last column transpose. Okay. I remind you the definition of the left null space is basically all the vectors y such that A transpose y equal to 0. So basically this is what I have written here. The only difference is my y now is this error B minus AX equal to 0. So what do I have here is, this is my A transpose. So let me write this, A transpose B minus AX equal to 0. So A transpose A X hat equal to A transpose B. And these are the very famous normal equations that you get when you project in the column space of a matrix. Now you can immediately recognize that to be able to compute this X hat, A transpose A has to be invertible. And if the columns of A are independent, the solution to this problem is given by this wonderful equation. All right, so this is the optimal solution to this problem. So X hat given A transpose A inverse times A transpose B. And if you want to compute now what is the projection of B on the subspace, it will be A times X hat, right? By definition, this is how we introduce X hat. So A times this would be the projection point. And if you're asking what is the projection matrix that does all of this, the projection matrix is A transpose A inverse times A transpose. So we have come really long way in the calculations with rather simple algebra that goes around this simple equation that you see here, that the error B minus AX is on the left null space, and then immediately we get all the results that we need for our particular problem. So let me just summarize and say a few things again for this problem. So we are, in principle, we're trying to solve AX equal B, and B is not in the column space of A. So we cannot really solve AX equal B, as you remember from earlier lectures. So what do we do is we're actually trying to approximate B with its projection on the column space. So instead of solving AX equal B, what actually we solve is we solve AX hat equal to the projection of B to the subspace, which we call it P. And that problem has the solution that we saw in the earlier slide, and I believe it's also summarized, more or less summarized here. So we compute from this equation X hat, okay, and A times X hat gives me the projection to the subspace. So you have everything you need for this particular problem. So keep in mind, the only fundamental equation I mean, there are two really things that we used. One is you need to recognize what it means to be in the column space, right? It has to be multiple of the columns. So AX hat is in the column space. And then we need to recall that B minus AX hat is in the left null space. And that's all. I mean, that's all we have used in this particular problem. All right, so let me do a simple example. I am trying to solve AX equal to B. A is given by this 3×2 matrix and B is given by this. You can immediately see, you know, whatever you do, you cannot solve AX equal B exactly because this vector B does not belong to the column space of A. And what that means is there's no way you can generate this vector B by taking linear combination of the two columns of A. You can try, but you will see that it's not possible. So what we will do is we will, you know, do the machinery from before, project B to the column space, form the normal equations and solve them. And this is what I have done here. I compute A transpose A. It's given by this nice matrix. I compute A transpose B is given like this, and you solve the normal equations for x hat. You get x hat equal 5 and minus 3, and then you know immediately that the projection point P is a linear combination with coefficients 5 and minus 3 of the two columns of A, which I remind you from the previous slide are 1, 1, 1 and 0, 1, 2, and this is what we, you know, I can see there is somewhere there must be a typo here, so I see here 5 minus 6 doesn't give you 1. So I'm assuming, so let's go back so we can actually correct this. So if this is correct, right? So we have 1, 1, 1 and 0, 1, 2, okay? So, so this would be 0, 1, 2. So 5 minus 3 is this to be let me see, there must be a typo here, okay? So, so the projection P here is 5, 2 minus 1, okay? So 5, 2 minus 1. So if this is 1, so this is supposed to be a 2, okay? So this is a mistake that we need to correct, and I'm going to revise the slides to actually represent this changes that you see here, okay? But the idea again is take the two column vectors. X hat tells you what combinations to take, and then you get this projection point. You define the error. And if you actually want to check if this error is correct, this error needs to be orthogonal to the column space. If you take the dot product of this with the first column, which if you remember was 1, 1, 1, you get a 0. If you take the dot product with the second column that was 0, 1, 2, you also get 0. So this, for certain, this error is correct in this particular case. So if you want to actually also compute the projection matrix P, you can do that as well. I gave you the formula in an earlier slide. So the projection matrix P actually comes to be the matrix that you see here. Again, it is symmetric. As we stated earlier, you can verify by multiplying P with itself that P squared is equal to P. And all of this, again, the fact that we can do all these calculations and define this projection capital P to the column space of A, it's an outcome of the fact that we assume invertibility of A transpose A. And I'm stating this again, that A transpose A is invertible because we assume that the columns of A are independent, or that the null space of A contains only the 0 element. So actually on this slide, I'm giving you sort of a trivial proof of that fact. So effectively, the slide proves that the null space of A and the null space of A transpose A are the same. So if the null space of A only contains the zero element, the same is true with the null space of A transpose A. And let me just highlight the proof very fast. If you take an X to be on the null space of A, you can multiply this equation by A transpose, and you can see immediately that X is also on the null space of A transpose A. You can do the reverse. If you take an X to be on the null space of A transpose A, you can multiply this equation with X transpose, and X transpose A transpose is nothing but the transpose of AX. And then from this, you can see immediately that AX has to be equal to 0. So X is in the null space of A. So again, this is a very important calculation. We need to assume that the columns of A are independent and the null space of A contains only the zero element. Otherwise, we will not be able to define this projection matrix P. I'm going to come back actually to this as to what potentially someone needs to do when the columns are not independent, but certainly the analysis we're discussing now will not fly. All right, so this slide, more or less, we stated together with the earlier slide. So when A has independent columns, A transpose A square is symmetric, it's invertible, and our analysis falls in place, and we can do all the calculations correctly. So let me give you an example of an A that has columns that are independent, and another A that has columns that they are dependent. So obviously you can see on this matrix A here, the two columns are the same. So when you do A transpose A, you can see A transpose A is singular, okay? Cannot invert this. So our analysis will not work in this problem, but if A has two columns that they are independent, A transpose A is invertible. So we are done. So let's provide a big summary, if you like, of the big picture. We want to project in the column space of A that consists of these vectors A1 to AN. So we approximate B with its projection in that space that is written here as a linear combination of these column vectors A1 to AN. We demonstrated how to compute X hat. This is by solving these normal equations. And once you compute X hat, you have the projection point of B in the column space of A. It's given by little p equal A times X hat. And from there, you have the error E, that is B minus AX hat. You can extract the projection matrix that is given by, are we missing on the projection matrix? Do we missing an A there? What do you think? So in our calculations there, right, we did, when we referred earlier to the least squares equations. So let's revisit this, right? So the projection matrix is AX hat, and X hat is A transpose A inverse A transpose B. So obviously there is an A here missing in this slide 26, and we're going to correct this in the slides that we post on the web. Okay. So we started really projecting on a line, and suddenly from a line now we can generalize and start projecting in a column space generated by taking linear combinations of vectors. If you look very closely at the results, actually they look practically the same. Here is the correct projection matrix that we messed up in the previous slide. The projection matrix is symmetric. p squared is equal to capital P, you can actually take this matrix here, multiply with itself, you will see that you will get immediately p squared equal to p. And of course, we call the projection of point B on the column space of A, we call it a little p. All right, so what I would like now to do is take a step backwards and revisit all of these things in the context of what people call in practice least squares methods or least squares approximations. Effectively, what we already have done is least squares approximation, but you maybe wonder, where is the least squares approximation? We don't see any least squares approximation anywhere. So somehow we need to be able to identify that our calculations are identical with the calculations that you usually hear in lectures on least squares. So let's keep moving and see how this is the case. So let me first give you a summary of this so-called least squares approximation that eventually is going to give us the same normal equations as what we have done already. So what's least squares? In least squares, basically, since you cannot solve AX equal B, you're saying, can you find some X hat that minimizes the error B minus AX hat? So you can think of least squares being as an optimization problem where your objective function is B minus AX hat and the unknowns are X hat. Obviously, to minimize this error, that's why we call this least squares error, we have to take derivatives with respect to the components of X hat, and we will do this. But the good news, actually, let me see if, so the derivatives are indicated here. So, if you have a vector with components, this X has components X1, X2, etc., you will set all of this equal to 0, and the equations, the linear equations you will get for X hat will come to be exactly the normal equations that we derived from geometry with a little bit of algebra. Okay, so least squares, really minimizing the error, gives you the same identical equations, but the interpretation can be a little bit different, but both imply exactly one and the same thing. So what we're going to do is one of the examples we're going to run through this part of the lecture will be to fit a straight line to a data set. So we're going to assume that, let's say, t is a time, and at different times, t1 to tm, we measure some variable that we call it b, and the measurements are b1 to bm. So we would like to fit a line, so that way we can do predictions using that line for every t, predict what the value of b is going to be. So if you put this measurement data in a matrix A, all right, you can see how a least squares problem is going to come. You are basically are going to have a matrix that we will see this in detail, but you are going to have a matrix that has a particular structure for this linear regression problem. But at the end of the day, we're going to show that for fitting a line, the matrix A transpose A takes this exact form. So M is the number of measurements. This is the summation of the times where we take measurements, and this is the summation of time squares. And A transpose B is this vector here. So effectively, we can solve this 2x2 system of equations and compute the two coefficients that define a line. So effectively, we're going to write B as being some constant, let's say, C plus another constant D times time T, and the least squares problem is going to compute for us the two coefficients C and D. Again, we're going to see this in detail shortly, but this is sort of the major application we're going to do in this part of the lecture. So I remind you again, the big picture we have seen up to now. Okay, what is that? We're trying to solve AX equal to B. All right, that's my equation here. B is not in the column space of AX, so there's no solution. So what do we need to do? Instead of solving AX equal to B, we're actually going to solve AX equal to P, where P is the projection of B in the column space of A. And if you evaluate then the error B minus AX, this error is in the left null space, and that gave us these normal equations that computes X hat, and then back from there it computes the projection of B to the column space of A. All right. So let's try to see these calculations. So I'm going to revisit these normal equations and provide a new interpretation on this fitting a straight line to a set of data. So my data will be 3 points. So the first coordinate is time, and let's say the variable B is the second component. So we're fitting 3 points to a straight line, and this is my equation of the line. And I have 3 measurements, and I want to basically compute 2 constants. Obviously you can write this in a matrix form the way we had it before. But before I do this, what I want to do is let me try to see if writing these equations precisely, right? So, we need to solve C and D so that we fit data. So let's fit the data. So for time 0, C plus D times 0 is supposed to be equal to 6. At time 1, C times D times 1 is supposed to be equal to 0. And at time equal to 2, C plus D times 2 is supposed to be equal to 0. Obviously, when you look at these equations, you have 3 equations with 2 unknowns. You cannot really solve them. And more importantly, if you see the system of equations that you get, the matrix has 1s on the first column and 0, 1, and 2 on the second. You can immediately see that the right-hand side 6, 0, 0 is not in the column space of that matrix. So these equations cannot be solved exactly. So whatever you do, there's going to be some error in the approximation. So the way we handle this problem up to now is define this matrix A, compute the projection of this B vector on the column space of A, and then solve the normal equations. And if you do all of this for this particular problem, you get a solution for least squares that looks X hat equal 5 and minus 3. All right, so I'm just doing nothing else, but I'm saying if I solve the normal equations, okay, this is what I get. All right, so if I get an X hat that is 5 and minus 3, I would like to use that to give you an interpretation that we have not yet seen in the geometric view that we followed for this least squares approximation. So what you see here is the line that best fits the data that is identical to these normal equations and the solution that we got with our earlier methodology. So this process are my 3 data points, all right? So the best fit here is B equal 5 minus 3t. This is an amazing sort of interpretation. If you think the 5 and minus 3, they give me combinations of the columns of A where my projection of B in the column space is, right? But now I use the 5 and minus 3 to actually fit this line in the way that you see on this nice plot. And the 2 interpretations are sort of complementary to each other. The you have to appreciate that these numbers 5 and minus 3 are actually the same numbers that we get by solving the normal equations, which is, A transpose AX hat equal to A transpose B. So let's see what these two interpretations are and what they have to say. So I remind you first the geometric interpretation we have seen. So this is the column space of the matrix. So in our case, the column space is spanned by two vectors. And the vector B that we want to solve AX equal B is not in the column space. So what we do is we project it in the column space. We compute the error E. We say that E has to be normal, it has to be in the left null space. And when we solve the normal equations, the projection point P is 5, 2, minus 1, and the error is 1, minus 2, and 1. Okay, so effectively these are the calculations we have done, and this is the interpretation we have seen up to now. So in principle, the idea here is that B is split in two components. One component that is on the column space of A, and another component that is perpendicular to the column space. That's the error E. And since we cannot solve AX equal to B, what we do is we solve AX equal to P, where P is effectively the closest, the best approximation we can find for B in the null space, in the column space of A. So this problem can be seen by using algebra as well, okay? And I am going to show you this in the following slide, but I wanted to write down this equation in a very general form, right? This is our original problem. We really want to solve AX equal to B, and the splitting that I show you geometrically of B to a vector in the column space and a vector perpendicular to the column space, this equation cannot be solved as is, right? So what we do is we say we're going to be committing that error E. There is nothing we can do about it. So instead of solving AX equal to B, let's solve AX equal to P. So we forget about the error E, and then the solution that we get for X hat is what you have up here, okay? So we can actually see this also in one slightly different form. You remember that B is P plus this error E that is orthogonal. If I can go back to show you a plot, right? The error E is orthogonal to the column space. So remember, if I look at the error AX minus B, the error AX minus B has two components. One, AX minus P, okay? And then there is the component E that is normal to the column space. So effectively, I can write this using Pythagorean theorem. AX minus B squared is the square of AX minus P, so this is in the column space, and the error E orthogonal to the column space. So you can think of the triangular formed by projecting B to the point P and taking any X, basically any combination of the columns that gives you this vector AX. So least squares, you know what it is you say, I really want to minimize this error, and to minimize this error, I need to find the best X to do that, and there is no X involved in this error E, all right? The only X that's involved is in here, and so the minimizer in here, the way we have seen it before, is to actually solve the normal equations and take and compute this x hat. Okay. You may want to actually, instead of doing this geometric and algebraic calculation that we have done, you can actually directly say, get me an x so that the error ax minus b square is being minimized. Okay, and it comes out again that the two calculations are one and the same. So basically, we can look at the whole thing as a geometric approximation with some algebra, considering that the error is in the left null space. And then we can also see this completely as a minimization problem where we minimize the square error ax minus b. All right. So if I can actually go a few slides back, I wanted to show you in this line interpretation. So this plot will be nice. So remember that this little vector p that we compute with our normal equations as ax hat, okay, this vector p, if we try to see what it means when we fit the best line, in this case the line 5 minus 3t, you can see, so this crosses are my data points. You can see actually the vector p has actually components that are directly the nearest points, if you like, of my measurement data points to the line. So P1 is this point here is equal to 5, P2 is this point here equal to 2, and P3 is equal to minus 1. So if you actually do the projection of B on the column space of A, you're going to find a vector that has components 5, 2, and minus 1, and suddenly you can see an interpretation of these points as effectively there being the 3 points on the line at the 3 measurement times that we consider, which is this time here, this time there, and this time there. So the 3 points at heights P1, P2, and P3 lie on a line in this particular case, and actually they do lie on a line because P is in the column space of A. All right, so we have a completely different interpretation on what this projection point P is all about, and we see this in fitting a line in this example. Now, you can also see, since I have this plot, you can see the error that you commit in each of the measurement points. So this is error E1 equal to 1, E2 minus 2, and E3 is equal to 1. You can actually, if you follow our normal equations and you compute B minus AX hat, you will find out that that has components 1, minus 2, and 1. So again, we have a geometric interpretation on our fitting a line problem of the error and the projection point P. So the two different views all coming with the same equations can be seen on these two plots. On the left, you fit the line. You see what the error means, what the projection point means, being the closest points to the line at the observation times, and you can see the geometric interpretation in terms of projecting in the column space and having an error orthogonal to the column space. You can see the two interpretations coming together, and of course both of them give you the same identical answer. And this least squares minimization problem is nothing else but really looking for the line that somehow minimizes the E1 square and E2 squared and E3 squared at the 3 observation times. So when you set the problem as the minimization of the error at the observation times, you actually do get the same identical equations as least squares. And I believe I have in one of the slides, maybe it's coming later on. I think I can see it's coming in a few slides, but I do actually have the equations that do the optimization problem just to convince you that provide the same normal equations as our geometric approach that we see here on the right picture on this slide. All right, so let me see if I can summarize the very general view of least squares. So we are trying to solve AX equal to B. That's our problem, okay? This problem has no solution because B is not in the column space of A. So we decompose B in 2 components, one P in the column space and another one E in the left null space. And instead of solving AX equal to B, we solve AX hat equal to P, where X hat is a point in the row space. And it's a point in the row space because I remind you that the null space contains only the 0 vector. We assume that the columns of A are independent. Okay. So again, AX equal to B is not solvable. AX hat equal to P is the problem that leads to the least squares type of approximation and to the normal equations that allow us to provide an approximate solution to this problem. Again, the null space, it doesn't come in the picture. So if you think that somehow any vector X in Rn can be written as a component in the row space and a component in the null space, this component in the null space for this particular approximation is 0 because of the independence of columns of A, but that's not the case with B that belongs in Rm. We split it in a point P in the column space and an error E that is in the left null space. So let me go back to the fitting the line problem so I can show you the optimization that I referred to you before. So we are trying to minimize at the M observation points the error squares. And remember, we're fitting a line C plus dt to my data. And so let's see how much error do we do at each observation point. So if there was no error, C plus D times T1 would be equal to B1, C plus DT2 would be equal to B2, and obviously, the optimal C and D that we're going to compute is not going to satisfy these equations exactly because B is not in the column space of this matrix A. Okay, and I think I showed you the equations leading to least squares for this fitting. So let me just write them down again. If you write down A transpose A and A transpose B for the normal equations, you get these nice equations that you see here. Okay, but really what I want to do here is I want to bring this error at each of the measurement times. So the error EI, that is BI minus C minus DTI. So if I can go back, we recognize these equations are not going to be satisfied exactly. So there's going to be an error, and this error, I call it EI. And this minimization of the error approach is effectively going to say, well, can you find the coefficient C and D so that this sum of square errors is minimized? And And that's why this method is called least squares error, right? We want to find an approximation that minimizes the square errors that we do at the observation points. So how do you solve this optimization problem? Well, so we want to find D and C, that this whole error objective function that you see in here is minimized. Now, you may forgot this from other calculus courses, right? If you have to minimize this function or to optimize in general, the first thing you need to do is you need to set the derivatives with respect to C and D equal to 0. And of course, there are optimality conditions you need to satisfy for the second derivative, so we're not going to bother in these lectures. But if you set the first derivatives with respect to C and D equal to 0, you can immediately see that you will get a linear system of equations for C and D, because this is squared, so when you take derivatives, the 2 is going to come down, so derivatives with respect to C and D will give you linear equations for C and D, and surprise, surprise, these linear equations are basically the normal equations, okay? And you can verify this in the slides. So if I go actually to slide 50, you can see that I was hoping actually the slide 50 will have the equations for the minimization problem. So obviously I don't see them. Maybe if I can go back. Well, I don't see the equations, but obviously you can recognize, right? If you take derivative with respect to C, for example, from the first term, you're going to have 2 times C plus dt1 minus b1 times 1, all right? And similar contributions from the other terms. If you take derivative with respect to D, you're going to have 2 times this whole parenthesis times time t1, and similar terms from all the other parentheses. So when you add all of these things, all the derivatives with respect to C equal to 0 and with respect to D equal to 0, and you assemble these equations, you do get the normal equations. And for the particular example that we're considering, if you can demonstrate this, you can actually take your own straight line problem, take 3 data points 3 different times, and give some values to B, and you can solve and verify that actually you understand how this least squares approximations work for this problem. So what I want to do now is I want to give you sort of a trick that is normal to least squares type of approximations that has to do with centering your data. So before I say much about centering the data, let's look at the least squares equations that we get, the normal equations, when we have these 3 measurements at times that the 3 time measurements sum to 0. Okay, so you can see actually my the times that I provide data are centered. Okay, so in this case the system of AX equal to B will look like what we have here. Okay, so this -2 and 0 and 2 are my times, and if you do least squares in this particular case and you form the normal equations, you get something that is not surprising. You get that the off-diagonal coefficients on A transpose A are equal to 0. And this is not a surprising result. It has to do with the fact that when you take dot products, I mean, what is A transpose A? You have to take dot products between columns of A. So the zeros have to do with taking the dot product, the inner product between, let's say, the first column and the second column, or the second column and the first column. So obviously, in this case of normalizing, of centering the data, this inner product is equal to 0. And that's why you get this nice A transpose A. And this is very nice because now you don't really have to invert any equations, because this is a diagonal matrix, and you can say right away that C is 7 divided by 3 and D is 6 divided by 8. So again, these zeros come from the fact that these dot products involve columns of A that they're perpendicular to each other. Now, how do we make actually the columns of A to be perpendicular to each other? And for this linear regression problem, one of the easy ways to do this is to compute the average time t hat, and then do regression, fit a line to a new variable, capital T, where capital T is defined T minus the average time. So in this case, when you sum all your observations in capital T, all right, at the 3 different capital T times, you will actually get you will get 0. And so in this particular case, if you repeat this and you try to fit a straight line in capital T time, your new matrix A is going to look like this, or these are the center times. And you can see immediately that A transpose A leads to a diagonal matrix. And then, of course, you get the results that I showed you in the previous slide. And you need to remember that once you compute your coefficients C and D, you have to go back to the original time scale that you use. And the time here, capital T, is T minus 3. Okay? So you have a nice equation that looks like this. Of course, fitting a line, it's an easy example. You can start doing magic and ask yourself, can I fit a parabola with 3 coefficients? Of course you can. And so we have 3 unknowns here. So let me do the following example. I'm going to fit a parabola with, well, the general case, my A matrix is going to look like this. So I have m time instances, all right? So each row is 1 t and t squared at each of the times. Okay, so you can do your least squares normal equations, and then you can compute the coefficients C, D, and E for your fitting a parabola problem. So, obviously you can, if you want, you can do this with a minimization of the error. And as we said, you will get exactly the same answers as before. But I want to do one particular example. So I'm going to fit a parabola, but I'm going to use 3 time instances. So I have 3 unknowns. I'm going to take 3 measurements, and the measurements are 6, 0, and 0 at times 0, 1, and 2. So I'm going to write the equations pretending that I can fit them exactly. So obviously, in this case, because I have 3 equations with 3 unknowns, you can actually show that the columns of matrix A are independent. So I have 3 of those, and if those 3 columns are independent, they span the whole of our cube space. So it doesn't really matter what B is. In that case, there is a unique solution to AX equal B. So yes, you can actually do least squares. You can compute and solve the normal equations. But what you will actually get in that case is the same solution as actually solving AX equal to B exactly. And in that case, the solution comes to be 6 minus 9 and 3. And my best parabola will be 6 minus 9t plus 3t squared. Okay. The idea here is there is no error, right? I have 3 equations, 3 unknowns. There is solution regardless of what my measurements are, because my 3 columns span all of R cube. And in this case, if I can ask, what is the projection matrix? If you do least squares, we said you don't really need to do least squares, but what's the projection matrix? If you're going to have to project B in the column space, but B is already in the column space. Every vector in R³ is in the column space, so the projection of B is B, and the error is equal to 0, and the normal equations are basically nothing new but solving AEX equal B. Of course, if you make things interesting and you suddenly add a fourth point, then you have no choice. So if you go and add a fourth measurement point, as is shown here, if this is your new B, then of course you're going to have to solve the least squares equations. AEX equal to B has no exact solution, and you can do the normal equations that we see again and find the best approximation for this particular problem. All right, let's continue. And I want to bring back this concept. What if the columns of A are not independent? Obviously, we said the least squares approximation will not work. So can we say something about even elementary on what does somebody supposed to do? So let's see an example. So let's say that our system of equations look like that. Obviously, you notice here the two columns are the same. And actually, if you think of this on fitting a straight line to the measurements B, so the line is C plus dt, the two times where I provide measurements are identical. So effectively, it's like having two different measurements on the same time t equal to 1. So I do two measurements at the same time, leading to this singular matrix. Okay, and this is my vector. This is my vector B. So, so somebody will say, well, let's do the same ideas as least squares, which means let me project B to the column space. So that's what we have done. If you take this vector 3, 1, the column space is only the vector 1, 1. So really the projection of B is the vector 2, 2. So you say, okay, let me solve now this equation, say x hat equal to P. Well, unfortunately, you cannot solve these equations because the columns of A are not independent. And actually, you can see that the vector 1 minus 1 is in the null space, of A. So if you look for solutions to this problem, you realize all of these lines that you see here passing from the point at time 1 and measurement 2 are solutions. All right, so all of these points are solutions. Okay, so by the way, observe that x1 plus x2 is equal to is equal to 2. So at time t equal to 1, all of this lines that you see here. So if you think of the lines B written as x1 plus x2 times t, time t equal to 1, all of these lines will pass from the point x1 plus x2, which is equal to 2, okay? Because x1 plus x2 is equal to 2. So all of these lines are solutions, and you notice all of these lines commit an error at the measurement time that is either what is that? It's either 2 or minus 2. Or actually, I'm sorry, if this is 2, so the error is actually 1 or minus 1, okay? So this point, again, where all the lines are passing, is the point 2, so the error is either plus 1 or minus 1. All right, so the question then remains, what do you do? Which of these solutions is actually the best solution to select? and all of the solutions look sort of equivalent. All right, but which solution someone should choose? So someone will say maybe the best solution is to take this horizontal line. So if you take this horizontal line, it corresponds to basically, so if you think of B again being the line x1 plus x2 times t, means x2 equal to 0. This point here is 2, so x1 is equal to 2. So this solution is really my two coefficients in my straight line, c is equal to 2 and d equal to 0. Okay, now there's no really reason why that to be the short line. And the only thing I want to say, without elaborating much on this, maybe the best solution to this problem will not be to take the horizontal line, but instead take this line at 45 degrees that corresponds to x hat 1 and 1. And the reason this the solution that I denote here as x plus 1, 1 may be a better solution is because it's a solution that actually has the smallest length. So if you think of this as an optimization problem where you try to minimize errors, you can say, well, minimize the error while at the same time you try to keep the length of this vector x minimum. And so that minimum vector is the one that corresponds to the coordinates 1 and 1, because this has a length square root of 2. But the solution we saw before has a length that is equal to 2. Okay, has length equal to 2. In addition, there is, if I can go back on my previous slide, we mentioned to use this straight line that corresponds to the solution b equal to 2. But there is a pathology here, because we wrote our solution as c plus d times t. But if somehow you reverse the coefficients and you write the solution as d plus c times t, the matrix A doesn't change. I remind you the matrix A in this case, if I can find it, it's just the matrix 1, 1, 1, 1, right? Because the time measurements are taken twice at time 1. So effectively, if I change the interpretation of the variables, instead of getting, before I had c equal to 2 and d equal to 0, now with this interpretation and the same metrics, I'm going to have the opposite. I'm going to have, in this case, I'm going to have c equal to 0. And so this little c here is going to be equal to 0 and d equal to 2. So the solution of minimal length that I mentioned before avoids this problem. Okay, and if you're interested more about this, maybe later on when we discuss about the pseudo inverse of a matrix, we will discuss more about how this solution comes about. But for now, I'm going to bypass it and summarize basically these different interpretations we have seen for these squares. So we discussed from geometry and algebra how we derive the normal equations. We also discuss on minimizing the square error. And when you expand the square error, again, I did not do this rigorously, but you can see this is a quadratic function of x. So the equations you get are literally the same. You take derivatives of this with respect to the vector x or with respect to its component, you will see the equations that you do get are the normal equations. So the normal equations actually minimize the least squares error. The two approximations are one and the same. Okay, So let me move forward. This has been a very long lecture. So let me discuss about projections using orthonormal basis. So I'm going to introduce first a set of vectors, Q1 to Kn, and I'm going to call them orthonormal when the inner product between any two of them is 0, and when the length of each of these vectors is equal to 1. So the equation basically that summarizes this is Qi transpose Qj equal to delta Ij. So when I and j are the same, the magnitude of each vector is 1. When I and j are different, these vectors are orthogonal to each other, and I can write this in a nice form as Q transpose Q equal to I. So remember that when I write these vectors as orthogonal vectors, if you think of this being the column of a matrix, this matrix is not a squared matrix in general, okay? But still I can talk about the orthonormal columns of a matrix. Now, if it happens that this matrix Q that consists of this orthonormal vectors Q1 to Kn is square, then not only Q transpose Q equal to I, but also Q transpose equal to I. So immediately you can see now that Q transpose is equal to Q inverse, all right? And in that particular case of a squared matrix, we call this matrix an orthogonal matrix. So it sounds a little bit confusing here. So orthogonal matrix refers to squared matrices that basically have orthonormal columns, all right? And for those squared matrices with orthonormal columns, not only Q transpose Q equal to I, but also Q transpose equal to I. And we have this very interesting property that Q transpose equal to Q inverse. Okay, so why do we care about orthonormal vectors and these orthogonal matrices? Because if somehow we are talking about doing least squares and projecting in the column space of an orthogonal matrix, all the least square calculations become trivial. And I remind you, for example, the solution of least squares x hat was A transpose A inverse, but A transpose A phase Q is equal to the identity. So the only thing you get is, so here we're supposed to have A transpose A inverse times A transpose B, so we only get Q transpose B. So very simple calculation, okay? And then the projection matrix that you get, you remember the projection matrix is basically A times x hat. So A in our case is Q times x hat, so you get Q transpose B, and so our projection matrix is Q transpose, okay? Again, when I do this least squares approximation, I am not assuming that the matrix Q is square, but immediately you can see that if somehow Q is a square matrix, then my projection matrix becomes the identity matrix. The idea here is if you have a square matrix with orthonormal columns, then these columns have to be independent, so the matrix is invertible. So basically the projection of B to the column space is B itself, and least squares gives you the same solution as solving AX equal to B, or in our case, QX equal to B. Okay, this is a very fundamental concept. We're going to talk about Gram-Schmidt orthogonalization, and effectively the problem will be if I give you a bunch of vectors A1 to AN, can you somehow, assuming of course that these vectors are independent, can you derive a set of orthonormal n vectors out of them? And so the Gram-Schmidt orthogonalization works in sequence, one vector at a time, trying to orthogonalize the original vectors. And the way it does this, it selects one of the vectors and normalizes it and defines that as being this vector Q1. And then to define Q2, it takes the vector A2, but it removes its component on the vector Q1. All right. So basically, you're trying to find a vector, a component of Q2 that is orthogonal to Q1. And more generally, when you try to define Q1, you have to subtract from AI the projection of AI in the subspace that is spanned by the vectors Q1 to Qi minus 1. So you basically have to project your vector AI in the subspace of Q1 to Qi minus 1. And that projection, actually using this formula that you see here, it's the orthogonal projection that you see in this equation that may resonate with you. Okay, Q1 to Qi minus 1 are orthogonal, and these are the projections in each of these directions of Q1 to Qi minus 1. At the end of the day, we go from A to an orthogonal matrix Q that has orthonormal columns, and the matrix that connects A and Q is an upper triangular matrix that we call it R. So here is a new factorization of a matrix A to Q times R. And what is interesting here is that this matrix R is upper triangular because the I'm losing my voice talking for too long. So what is interesting is that this R is upper triangular because the we are doing this in sequence, and you notice this vector Qi, it somehow AI depends on all the vectors Q1 up to Qi, okay, not from the vector Qi plus 1. So when we take in a product of a vector, when we take an inner product of Qi, so let me identify what slide is this so I can show you this right away. So when we take basically an inner product of later Qs with earlier AIs, that inner product is 0. And that's why this matrix comes to be an upper triangular. I'm going to show you the derivation again. Right for now, keep in mind that somehow this sequential way of doing this Gram-Schmidt orthogonalization leads to an R that is an upper triangular. Right, so this is a very important factorization of a matrix A, and so we will see a little bit more details as we move along. Okay, so we go back to expand on the summary slide that we just saw. So we take an orthogonal, so we have a matrix Q, so let's not make it a square matrix. So it's a general matrix Q that has orthonormal columns. So we are assuming that Qi Qj equal to 0, and the magnitude of each of these vectors is equal to 1. And in this case, we call these vectors orthonormal, all right? And this you can actually show right away that if these vectors are orthonormal, then they actually form a basis, right, for the column space. You can use the definition of independence of these vectors and see immediately that the orthogonality implies independence of this of the column space of this matrix. So we have a matrix Q that has these orthonormal vectors, and we effectively the fundamental property that we have in place is that Q transpose Q equal to I. And you can see this when you take the Q transpose Q, you get ones in the diagonal because each of these vectors has a unit magnitude, but of the diagonals you get zeros. So Q transpose Q is equal to I. It is true regardless if this matrix Q is square or not, right? So it's the same result. Now, if it happens that somehow this matrix Q is also square, then we have Q transpose equal to Q inverse. Okay, we stated this before. So the inverse of Q is its transpose. So in addition to Q transpose Q, we also have Q transpose equal to the identity. Okay, so Q transpose is equal to the identity, and this matrix is called an orthogonal matrix. I mean, in some textbooks, maybe people will use the orthogonal matrix even for matrices that they are not square. But here, well, when we say orthogonal, we imply square matrices. So let's see a few examples of orthogonal matrices, starting with rotation matrices that you may be familiar. So you can see this matrix Q that when you operate a vector on it, it rotates the vector by an angle theta. So you can right away actually verify that Q transpose is equal to Q inverse. You can multiply the two things, you will see you get the identity matrix. So let me show you some geometric interpretation. If you take Q and you multiply with the vector 1, 0, you will get basically the first column cosine and sine. If you take Q and you multiply with the vector 0, 1, you will get minus sine theta, sine cosine theta. Obviously, I see a typo here, all right? So we need to correct this on this slide. So that's our rotation matrix. It's an orthogonal matrix. In this case, is a 2 by 2 matrix. I'm looking at vectors on the plane. Actually, the fact that Q inverse, if you think Q rotates vectors by an angle theta, Q inverse has to rotate them by an angle minus theta. Okay, and from there you can actually see immediately that Q inverse is Q transpose. So if this equation was correct, cosine theta, and you put theta equal to minus theta, this will become plus sine theta, and this will become minus sine theta, which is what you see up here on the right. Another set of orthogonal matrices that we have spent a lot of time in this course are permutation matrices. And so what you see here is a permutation matrix that takes XYZ and gives me YZX, or it takes XY here and gives me YX. So here in the first row, I have column 2, and in the second row, I have column 1. So I went from 1, 2 to from the identity matrix to 2, 1, and similar in idea with the permutation matrix on the left. So these matrices, I mean, you can see that they are orthogonal because they contain 1 and this 0. So if you take two columns and you multiply them, you get 0. You can see they have a unit length. And you can verify that Q inverse is Q transpose. And you can actually literally, if you can, so if you permute this and it takes you to this vector, you can now multiply this with Q transpose, and you will see that you go back to X, Y, and Z. And I think this is exactly what I have done in here. All right, so I can see I take the vector Y, Z, X, and I multiply with the transpose of this permutation matrix. So 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, and then this takes me back to x, y, and z. So Q minus Q inverse is equal to Q transpose. You can have reflection matrices around a vector U. So if you want to reflect any vector around this line parallel to the vector U, the reflection matrix that allows you to do that is this interesting matrix that is the identity minus this rank 1 matrix that is 2 times U transpose. I'm not going to repeat the algebra on the slide. It's rather straightforward. You can see that this reflection matrix is orthogonal, and you can verify that Q transpose is Q inverse. You can verify that, like we expect in projection matrices, that Q square is equal to the identity. And also, you can verify that if you try to take a reflection of a vector that is parallel to the vector U that we use to define this reflection matrix, you will see that this matrix doesn't do anything to U and it leaves U alone. So let me see if we have an example on the next slide. So if you take U, a vector, in the direction of 45 degrees, and you try to do reflection. So this is how Q looks like. Okay, so I minus 2 times U transpose, you get something like that. So you can immediately see if you apply this reflection matrix to the vector xy, you get yx. So effectively, x is reflected to y, and y is reflected to x. You can, again, if you take a vector that is in parallel to this line on 45 degrees, like the vector 3, 3, you will see that this particular reflection matrix doesn't do anything, and it leaves things completely unchanged. All right, a very fundamental now concept about this, orthogonal matrices. So orthogonal matrices, if you operate with them on vectors, they have two things. They don't change the lengths of vectors. So the length of qx is the same as the length of x. And if you take the inner product between two vectors x and y, the angle between those two vectors doesn't change, which means that qx transpose qy is the same as x transpose y. And the proof is given in the slide, is rather simple. So for example, qx transpose qy, you can see taking the transpose of a product here is x transpose q, and q transpose q is the identity, and again, doesn't have to be squared here, but the x transpose y basically is the same. The inner product is the same as the inner product between qx and qy. And the same thing about the lengths. The length of qx is the same as the length of x. Now, I mentioned this already, why we're interested on working with orthogonal matrices. So if we do least squares and if we're solving AX equal to B, basically an A is an orthogonal matrix, our least squares approximations are being simplified enormously. So the A transpose A becomes Q transpose Q, and Q transpose Q is equal to the identity matrix. So the projection matrix becomes Q transpose. The optimal least square solutions becomes Q transpose B, okay? And the projection vector in the column space of Q becomes Q times x hat. And I want to actually expand, if I can, on this equation a little bit to see the geometric interpretation of things. So remember that in this case, the projection is Q times X hat, and X hat is basically Q transpose B. So each of the components of X hat is Q1 transpose B, Q2 transpose B, etc. So let me rewrite this vector P explicitly. And so if I write this vector P explicitly, this is what you get. You basically, you remember this, we had Qx hat, and X hat is Q transpose B. So this is my Q, and this is my X hat. So effectively what I have done is I have written P is the projection of B in the subspace of Q1 to Qn, and because these vectors are orthonormal, the projections in each of these vectors is Q1 transpose B, Q2 transpose B, Qn transpose B. So this is really your very familiar expression in projecting a vector to an orthonormal basis. Okay, this is extremely important. Okay, so let me make it even more fascinating. Let's take that this Q matrix now is a square matrix. If it is a square matrix, the vectors Q1 to Qn basically form a basis for Rn. So basically, the AX equal B system has a solution for any B. The projection of B in the column space is B itself. The projection matrix is the identity. And effectively, what I have written here is Q1, Q1 transpose, Qn, Qn transpose. If I sum all of these projection matrices, I get the identity matrix. Okay, so effectively, you can think of, in that particular case, splitting a problem, decomposing the problem into components, one contribution from each of the vectors Q1 to Qn, and then sum them up to get, in the case that we discuss, B back. Okay, so again, this is when Q is square. If Q is not a square, this is what gives you the projection of B in the column space of capital Q. But if Q is a square, this equation basically, it gives you B because B is already in the column space. So Q1, Q1 transpose plus Qn, Qn transpose has to be the identity matrix. Okay, and actually that's exactly what I have written here. In that case, the projection matrix P is equal to Q, Q transpose, which you can see it written in components as a summation of Qi, Qi transpose for all i's. All right, so let me do an example. Okay, and so what I'm going to do is I'm going to take an orthogonal matrix. You can verify that the columns are orthogonal here. So Q transpose Q and QQ transpose equal to I. So I have literally three independent columns. So they form a basis for R cube. So it doesn't matter what B is, there is always a solution. So the projection of B on the column space of capital Q is B itself. But let's see it. If you take the projection of B in Q1, you get this. If you take the projection of B in Q2, you get that. And the projection of B in Q3, you get that. And if you go and you sum up all of these contributions, effectively you can verify by doing the algebra. So this is your first vector Q1, this is vector Q2, this is vector Q3. These are the projections of B in each of those three vectors. If you sum up these contributions, you get, no surprise, B itself. So effectively what this decomposition does, if I can go back, it says take the vector B and decompose it in a component on the vector Q1, in a component on a vector Q2, and a component on a vector Q3. This expression here is exact, and it gives us back B itself, because these vectors span the whole R cube space. In general, when we do least squares, that would not be the case. So we really have to do orthogonal projection in the column space of Q. But here, that projection is basically the identity matrix. All right, I think we're moving along, and I'm looking forward to the completion of this lecture. So let's discuss about the Gram-Schmidt orthogonalization. So we can finish it up. So I'm giving you the following situation. I'm giving you three vectors A, B, C, and I tell you compute me three vectors capital A, capital B, capital C that they're orthogonal to each other. And actually, if possible, make these vectors to be also orthonormal, so effectively divide by their magnitudes somewhere in between or at the end of the process if you want to do that. So the procedure that does this is extremely fundamental to linear algebra, and it's called the Gram-Schmidt orthogonalization process. So let's see it geometrically. So I'm going to start with a vector capital A to be the same as A. Okay, so nothing fancy there. And so I'm going to take now the vector B, the little b that I'm given. And this is the vector little b. And so I want to get something that is orthogonal to capital A from this little b. And the way I'm going to do this is by removing from B its component in the direction of capital A. So I'm going to take this B vector and subtract this projection P that you see on the previous vector capital A. And that way I'm going to get my capital B. Okay, so I now have a capital A and a capital B. I'm taking my third vector C. Now I want to make it orthogonal now to both capital A and capital B, or equivalently, I want to make it orthogonal to the subspace that capital A and capital B span. How am I going to do this? I'm going to take the projection of C in the plane of A and B, and I'm going to define a vector C by subtracting from little c that projection. And you keep going and going until you finish with all your vectors. At the end, you can divide by the magnitudes, define these unit vectors, and the procedure is basically complete. Okay, so here is with equations, the vector capital B is defined by taking the vector B and literally removing the projection of little b on the vector capital A. Okay, and we have seen this in earlier in this lecture. If you want to see explicitly the equation for capital C, basically you take C and you have now to remove its components in the vector capital A and the vector capital B. Remember, these are not the vectors little a and little b, they're the vectors capital A and capital B that we already have made orthogonal. Okay, so this is the vector capital C, and so we operate one vector at a time, and every new vector has to be orthogonal to the space spanned by the vectors we already operated and we orthogonalize in the earlier part of the procedure. So let me throw you one example. If you have these three vectors that they are obviously they're not orthogonal, so you can start with capital A being little a. You can define B by removing its projection on capital A, so you get this nice vector. And then you can define C by removing its projections on capital A and capital B. And the algebra is shown here, and the vector capital C is there. And at the end of the day, you can orthogonalize this, and these are the three vectors, Q1, Q2, and Q3. So this is Gram-Schmidt orthogonalization, and let me just finish the whole lecture today by putting this Gram-Schmidt process in a way that will allow us to connect now the matrix capital Q that is defined by this vector little q's as columns, So I'm going to try to find a way that connects my original matrix A with this matrix capital Q that is, involves vectors that they are, that we have orthogonal, or actually have make them orthogonal and normalize them as well. All right, so let me go directly on slide 85. And remember, we started with a matrix A that involves these vectors A, B, C. We computed these vectors Q1 to Q2, Q3. And the question is, what exactly should I put there, all right? Should I put there that connects the two matrices? And I want to do it indirectly, but without using the Gram-Schmidt orthogonalization. But you agree with me that Q1 was related only to A, and A was related only to Q1. So if you do the multiplication, you can see that Q1 times Q1 transpose A, if this equation is correct, it's supposed to give you the vector A. So really Q1 transpose A is the magnitude of A, because Q1 is normalized, okay? And again, Q1 and A are in the same direction, so this equation looks correct, right, when it comes to A. Now, let's look on B. So the way we derive the Gram-Schmidt orthogonalization, Q2 was dependent only basically on A and B. So equivalently, B was depends only on Q1 and Q2. And this is exactly what this equation says, that the vector B is Q1 times Q1 transpose B plus Q2 transpose B. So these are the orthogonal projections of B in the vectors Q1 and Q2. Notice there is no contribution from Q3 because the vector B is in the same subspace as the vectors Q1 and Q2. I mean, at the end of the day, the subspace generated by A and B is the same as the subspace generated by Q1 and Q2. The only difference is Q1 and Q2 are orthogonal to each other. So basically, I'm projecting B in the orthogonal subspace, in the subspace generated by Q1 and Q2, and this is Q1 times Q1 transpose B, and Q2 transpose B. There is nothing from Q3 because Q3 hasn't come in the picture when computing Q2, okay? You can actually see this in another way. If you look at this decomposition, AQR, where R is this upper triangular matrix, you can see that R is Q transpose A. So effectively, if you let's look at this component here that is missing, all right? So according to this equation, this is the component 2,1 of R, and the component 2,1 of R is really we have to multiply Q transpose by A. So we have to take the second row of Q transpose and multiply it with the first column of A, and the first column of A is the vector A1. So again, we have to multiply the second row of Q transpose. And what is that? That is the second column of Q. So we have to multiply, to get this element there, we have to multiply the second column of Q, which is Q2 transpose, times the first component A1. So we have to calculate Q2 transpose A1. But you remember, Q1, A doesn't depend on Q2. So Q2 transpose A is equal to 0. So the idea here is that when you take inner products here that involve later Qs, And so when you take these inner products with early arrays, the result is 0. So for example, again here, this is the inner product of Q3 with A, that's 0, and this is the inner product of Q3 with B. Those inner products are 0 because the later Qs are orthogonal to the early arrays by the design of the Gram-Schmidt orthogonalization. So again, we started with Q1 in the direction of A, then we proceeded with Q2 by removing its component on Q1 and making it so orthogonal to Q1. And then we defined Q3 by being orthogonal to the subspace bound by Q1 and Q2. And as I mentioned a few minutes ago, the subspace bound by Q1 and Q2 is the same as the subspace bound by A and B. So Q3 is orthogonal to A and B, and that's why these elements here are missing. So effectively, this is the QR factorization, and here is a simple example. This is my matrix A. This is my orthogonal matrix consisting of the Q vectors, and this is the upper triangular matrix. I am going to just state here as a fact from the way that the calculations have proceeded, these square roots that you see here are nothing else but the magnitudes of the Q vectors. Okay, so that's why you get lots of square roots. So in some sense, the QR factorization is not pleasant to work with. It involves a lot of square roots versus the LU factorization, but it is convenient because it allows us to actually do operations that take advantage of the orthogonality of the columns of Q. And a typical example is when we do least squares and we have to compute A transpose A. If you substitute A as QR, transpose times QR, you can see A transpose A becomes R transpose R, and the least squares equations take this form that you see here, which are actually equivalent to Rx hat equal to Q transpose B. And I remind you that R is an upper triangular matrix. So to compute X hat, you can do this extremely efficiently using back propagation. So you can start from the last equation and proceed up all the way to compute X hat n, all the way up to X hat 1. Okay, so the calculations are significantly simplified because solving this equation requires only calculations with an upper triangular type of matrix. So let me just complete this this very, very long lecture by stating that the way that we computed the QR factorization with using this Gram-Schmidt orthogonalization process, it's not the way that computer codes like MATLAB or LAPAC that are heavy in linear algebra will do the QR factorization. So effectively, for example, LAPAC, what it does is it uses what is called householder reflections, operating one column of A at a time to create this upper triangular matrix R, and the algorithm is way more efficient than the Gram-Schmidt orthogonalization process. Anyways, there is a conclusion slides at the end summarizing all the key things that we discussed. Fundamental thing here is looking at least squares as orthogonal projections on the vectors or this orthogonal vectors Q, and if it happens that the matrix capital Q is a square matrix, we identify that when we project on the vectors Q, we get B back itself. So this is the fundamental equation where we take a vector B and we decompose it in components in different coordinate systems, if you like, in different coordinate axes, to be more precise, in Q1 to Qn. And then at the end of the day, you assemble all of this. Things together. This idea of that is under this projection on this orthogonal vectors Q is obviously fundamental to linear algebra, and it's actually in the heart of doing Fourier expansions, as we will see later on in the course when we move out of the linear algebra subject area. All right, so that's all for today. So hopefully this lecture has been saved properly, and I will see you tomorrow for a lecture on another topic. Thank you.